Good evening everyone. Welcome to the fourth live interactive session for concrete technology. I am Sedu Vinayagam, a PhD scholar from the Civil Engineering Department at IIT Madras. We will get started with this session. Okay, so let's start with an overview of the lectures for week 4. So it had 3 lectures, right? So this particular module was focused upon mineral admixtures, right? So in week 3 we covered chemical admixtures, and week 4 was about mineral admixtures. So the first lecture gave us an introduction, right? So what are the different commonly used mineral admixtures? So those are fly ash, silica fumes, ground granulated blast furnace slag, and rice husk ash. So we then looked at the production process for some of these mineral admixtures, and also we looked at the different physical and the chemical characteristics, right? Like what is the size distribution, right? So what is the specific surface, specific gravity, what is the shape of these mineral admixture particles, and also the chemical characteristics in terms of like what is the percentage of different oxides present in these admixtures, and also some of the mineralogical characteristics. Right, so in the second lecture we looked at how the addition of these mineral admixtures, how does it affect the fresh state of concrete, right? So in particular we were looking at the hydration process of the different pozzolanic material, right? And then what is the effect of this mineral admixtures on the setting time of cement, and how will they affect the hydration, heat of hydration, as well as the water demand, right? So this has to do with the reactivity, and also how will they affect the pore size in the cement gel. And in the final lecture we looked at what is the effect or the long-term effect of these mineral admixtures. So in terms of that we looked at how will the water reducing agent requirement change, and what is the effect on bleeding, what is the effect on mechanical performance, such as we looked at how will it affect the strength development, how will it affect the elasticity modulus, and so on. And then we also looked at how is creep affected, and also the shrinkage, the drying shrinkage, and the durability of concrete affected based on using with respect to different mineral admixture usage, right? So based on these we look at some of the questions. So the first question is, what is the common thing in pozzolanic materials? Options are reactive lime, reactive silica, reactive alumina. Option D, nothing. Okay, so as usual I'll create a poll, and once you're ready you can answer in the poll. Okay, so the poll is launched. So when you're ready, please answer. Okay, we have one vote each for reactive lime and reactive silica. Okay, let's take a look at the answer now. The right answer is option B, reactive silica. Right, so in all the different pozzolanic material, it is they contain reactive silica. Right, so and by addition of these admixtures into as replacements for cement, so during the hydration, it is this reactive silica that will react with lime to produce the CSH gel, right? So that will contribute to the strength, right? So it is common. What is common is the reactive silica, right? Between all the different pozzolanic materials. Okay, so second question is, which of the following requires the maximum amount of energy for production? So the options are cement, lime, rice husk ash, and fly ash. Okay, we have one vote for option A and one for option D. Okay, so the right answer is option A, cement. Right, so the question was about which takes the maximum amount of energy for its production, right? So it's actually cement which requires the most energy, right? So about 372 kilojoules to produce 1 kilogram of cement, whereas fly ash is actually the least, right? So actually we get it by burning coal, right? So we are not really spending any energy to produce fly ash. It is collected after the combustion of it's obtained as a product of the combustion of coal, right? So we are not really spending much energy to produce fly ash itself, so it's almost negligible, right? So there is nothing we are spending. So it's cement which takes the most amount of energy, and therefore it is advantageous if you look at all the other pozzolanic materials. So they also take some amount of energy, but it is not as much as it requires to produce cement, right? So there is some advantage in terms of the energy requirements, like to replace or to substitute some fraction of cement with these pozzolanic materials, right? So just looking at in terms of the energy requirement alone, right? So there is some advantage. Okay, so moving on to question number 3. What is the effect of mineral admixtures on the initial and final setting time of cement? So the options are increases significantly, decreases significantly, no adverse effect, or significant effect.
Sir, very good evening.
Yeah, good evening. Okay, we have two votes, one for option A, increases significantly, one for option C, no effect. Okay, any other answers? Okay, so let's take a look at the right answer now. The right answer is option C. There is no adverse or any significant effect on the setting by the use of mineral admixtures, right? Um, so that's what we saw. So setting time, it doesn't mean that there is no effect. There is there will be some effect on the setting time, right? So it will slightly increase, but but it is not really significant. You will not see it be increased by large amount of time, right? So for example, if it takes 4 to 5 hours initially without any admixtures, like it can become maybe 4.5 5 hours after the addition of admixture, but it will not be like 24 hours, right? So it won't be that much high, right? So there is some effect, slight increase. Also it depends on the type of cement, right? So the effect will be different on different types, but it is not really that we need to worry about, right? So there is not any adverse effect, right? So that's why option A is not right. Option A says it significantly increases, but it only slightly increases, that it's not really that significant. Okay, so moving on to question 4. Which of the following mineral admixtures have the highest heat of hydration? So the options are fly ash, GGBFS, silica fume, and option D is all of them have the same heat of hydration. Okay, we have two votes for option C, silica fume. Any other answers? the right answer is C, silica fume, right? So it has the highest heat of hydration. So what is among all the different admixture that is given here? So why is that? So how what is the relation between the heat of hydration and the reactivity? So we already saw this, right? So from week 1 we are seeing that the highest reactive component that will release the most heat, right? So during its hydration process, right? So we saw this in the case of the OPC as well, where we among the different components it is the C3A that is highly reactive and had the highest heat of hydration, right? So similarly, among the admixture, silica fume is highly reactive and therefore it has the highest heat of hydration. And also this highest reactivity will be due to its physical and chemical characteristics, right? It depends on the specific surface and also the composition of the different oxides, right? How much silica is present, right? So based on these, silica fume will be more reactive than fly ash and GGBFS, and therefore it will produce the most heat quickly. Okay, so moving on to question number 5. Which of the following mineral admixture results in the increase in water demand? Again, fly ash, GGBFS, silica fume, and rice husk ash. Okay, for those who join late, we have a poll going on after each question. So you can answer, give your answer for those questions in the poll. The poll will be under the activities option in your Google Meet screen. If you open the activities option, there will be the poll and you can answer in that.
Sir, my answer is silica fume, sir. C.
Okay. So you can make use of the poll to give the answer. So we will be able to see the distribution of answers. There is one vote for option C, one for D. Okay, I'll wait for one more minute if there are any other answers. answers? Alright, so we'll take a look at the right answer now. So the right option is option D, rice as cash. Right, so when we are talking about water demand, right, so it depends upon how fine the admixture particles are, right? So if you remember the physical characteristics, so we saw that the fly ash has spherical particles, but the size is not too fine, right? So GGBFS has irregular shaped particles. Silica fume is fine, but rice as hash has the most specific surface, right? So it has the highest specific surface among all the four, and therefore it will result in an increase of water demand, right, to a large extent, like come in relative to the other three, right? So therefore, rice as cash is the right option. Okay, so question number 6 is which of the following mineral admixture requires the highest dosage of superplasticizer? So the options are the same: fly ash, GGBFS, silica fume, and rice as cash. So this is related to the previous question. There is one vote for option D. Any other answers? Okay, one vote for option C. Okay, shall we look at the answer now? Any more votes? Okay, so the right option is option D, rice as cash. Right, so as I said, this is related to the previous question, right? So in the previous question we saw about the water demand, right? So we saw that because of its high specific surface, rice as cash increases the water demand, right? So it increases the water demand by a large extent than the other admixtures, right? So because of this increased water demand, right, so how do we compensate for this increase in water demand? So we can use super plasticizers, right? So because the water demand is increased the most by rice as cash, the demand for the super plasticizer will also be more for rice as cash, right? So these two are related. So when you want to reduce your water requirement, so you go for super plasticizer, right? So therefore rice as cash will increase the amount of super plasticizer that you need, right, than the other three, right? So therefore option D is the right one. Okay, so question 7, which of the following mineral admixtures result in less creep? The same four admixtures: fly ash, GGBFS, silica fume, and rice as cash. We have two votes for option C. Any other answers? Okay, let's take a look at the answer now. So the right option is option C, silica fume, right? So it reduces creep the most, right? So why? Because what is creep? It is creep is the deformation that you see when concrete is subjected to a sustained load, right? So you apply a load, keep that load constant, so over time, so there will be some deformation, right? So the load is the constant, but there will be deformation that will keep on happening, right? So that deformation taking place under the sustained loading condition is called as creep, right? So so among these four, silica fume will can give you the highest strength for concrete. So when you as an admixture, so this will give you the most strength among others, and therefore with higher compressive strength you will be able to reduce the effect and reduce the creep that you see in the concrete, right? Therefore silica fume will reduce the creep the most. Okay, so question number 8 is, which of the following is a point of concern and should be taken care of while using silica fume as a mineral admixture? So the options are strength, creep, shrinkage, none of the above. There are 2 votes for option C, shrinkage. Any other answers? Okay, so let's take a look at the answer now. So the right option is option C, shrinkage. Right, so we already saw, I already told that silica fume will give you higher strength. It will also reduce creep, right? So it is actually advantageous in that sense. But with respect to shrinkage, it's a point of concern, or it's not. It's going to increase your shrinkage, drying shrinkage, right? So therefore, it is disadvantages in that sense, right? Therefore, that is something that we should keep in mind when we are going for silica fume as an admixture, right? So it gives you higher strength, lowers your creep, but it will also increase your shrinkage. Why? Because it affects your porosity. So the gel pores will be reduced by the silica fumes, right? And therefore the capillary also the capillary water will be taken by it, right? Therefore there will be more shrinkage that you will see in the case of silica fumes. But there are measures that you can take to counter this, right? So one thing that you could do is do good curing, right? So you do enough curing so to compensate for this shrinkage that you see, right? So but that is a point that we should keep in mind. Okay, so question number 9 is, which of the following has the highest amount of silica? So the options are type C fly ash, type F fly ash, silica fume, ground granulated blast furnace slag. We have one vote for option C, silica fume. Any other answers? Okay, one vote for option B, type F fly ash. Okay. Any other options? So let's take a look at the answer now. Okay, so we are talking about silica, which has the highest amount, right? So among the four, as the name suggests, it is silica fume that has the highest amount of silica present in it. So if you look, remember the chemical composition, right? It was taught in the first lecture of week 4. So we looked at among the four types of fly ash. So we have silica fume, which has a large portion of it having SiO2, right? So it is more than 80% of silica fume is silica only, right? So whereas compare that with others, type C fly ash has only about 25 to 50% of silica, type F about 35 to 60%, and GGBFS has about 20 to 40%, right? So whereas in silica fume you have more than 80% of it composed of silica, right? So therefore option C, silica fume, is the right option. Okay, question number 10, which of the following statement is correct? So there are 4 statements given. Type F fly ash has more calcium oxide than type C fly ash. Option B, type C fly ash has more calcium oxide than type F fly ash. Option C, both type C and type F have less calcium oxide. Option D, calcium oxide is absent in both type C and type F fly ash. Okay, any answers? Okay, we have one vote for option B. Okay, any other answers? Okay, so let's take a look at the right option. So right option is option B. Type C fly ash has more calcium oxide than type F fly ash. So again we go back to the chemical composition, right? So we already saw which has the highest SiO2, right? But with respect to calcium oxide CaO, so we are comparing type C fly ash with type F, right? So type C fly ash has about 10 to 40% of it as CaO, whereas type F has only about 0.5 to 10% of it composed of calcium oxide, right? So clearly type C has more calcium oxide than type F, right? So that both are fly ash only, but depending on the calcium oxide content, we are saying there are two types and one type has much more than the other, right? So among the two, it is type C which has the highest concentration or composition of CaO. So question number 11, which of the following mineral admixtures lowers the heat of hydration? So options are fly ash, GGBFS, silica fume, option D, all of the above. Okay, so this is multiple answers, multiple choice, multiple answer questions, right? More than one option can be correct, right? So you can choose accordingly in the poll. Okay, so I have created a poll for options AC, BC, AB, or option D. Okay, we have one vote for options A and B. Any other answers? Okay, let's take a look at the right option now. See, the right answer is options A and B, fly ash and GGBFS. So both will reduce the heat of hydration, right? So we already saw that silica fume will increase your heat of hydration, right? Because it has so what does it have to do with? So it has to do with the reactivity, right? And that is dependent upon the specific surface, right? So the more fine the particles are, the more they could react, right, during hydration, right? So silica fume, if you look at the specific surface of the different admixtures, you see the fly ash, both type F and type C, they have about 1.5 to 3, whereas GGBFS also has about 2 to 4. Compare that with rice husk ash and silica fume. So they have much higher specific surface, 50 to 100 for rice husk ash and 15 to 25 for silica fumes, right? So those two are highly reactive, whereas fly ash as well as GGBFS, because of their lower specific surface, their reactivity is not as high as rice husk ash and silica fumes, right? And also we are talking about, but we are not talking about reactivity, but about the heat of hydration, but those two are again related, right? So the one that reacts fast will also produce high heat of hydration, right? Whereas because of their low reactivity, they take a long time to react, the heat of hydration will also be lower, right? It will be spread out over a long period of time, right? So they won't give very high heat of hydration, and therefore the right options are fly ash and GGBFS. Okay, question 12, it's true or false. So adding mineral admixtures to cement can affect air entrainment. So is this statement true or false? Any answers? Is this a correct statement? Okay, no response so far. Okay, shall we look at the answer now? Okay, there is one vote for option B, false. Okay, any other answers? Okay, so let's take a look at the right answer now. So the right answer is actually, it is a true statement, right? So the statement that it affects air entrainment is true, right? So it's not just for anyone. All the admixtures will affect your air entrainment in the cement, right? So what is the effect? So the effect is that they will reduce the air content, right? So the degree of reduction is dependent upon the admixture that is used. It varies, right? So like silica fume has silica fume, there is fly ash and slag, so the amount of reduction is different, right? So this control is your cement without any mineral admixture added, and then we are comparing it with others and we see a reduction, right? So there is an effect and it reduces, and therefore the statement is true. But why is it reducing the air content? Because we saw that the admixtures will affect the porosity of the cement, right? So the void content will be affected by the addition of the admixtures, right? So when you have a reduction in the porosity, your air content or the air entrainment will also be affected, right? And therefore we see a decrease in the air content, right? So therefore the statement was true, and the effect is that it will decrease. Okay, so question number 13 is, which of the following is not a common aspect of pozzolanic materials? The options are, they are reactive in nature due to their relatively high chemical potential. Option B, these materials react with lime in presence of water to yield CSH. Option C, these materials are having amorphous siliceous and aluminous content. Option D, all pozzolanic materials such as fly ash, rice husk ash and GGBFS are spherical in shape. Right, so you have to choose the option which is not correct. Okay, we have 2 votes for option D. Okay, any other answers? Okay, so let's take a look at the right option. So the right option is option D. All pozzolanic materials such as fly ash, rice husk ash and GGBFS are spherical in shape, right? So that is the one aspect given among these that is not same or not true, right, of the pozzolanic materials. Why? Because the shape changes depending on the admixture used. So the spherical ones are actually the fly ash and silica fume, right? So only those two have spherical, whereas rice husk ash has cellular structure, GGBFS is angular and metakaolin is platy, right? So this size is not the shape is not the same, right? So it varies depending on the admixture used, right? So therefore D is the one that is not common. whereas the other three are correct, and it is same that the effect that or the statement that is given is true for all the admixtures, right? So one is they are reactive in nature because of their high chemical potential. That is true because the way these admixtures are produced is that they are produced when by exposure to high heat and rapid cooling, right? So because of that, they have lot of chemical potential that is stored, and that gives them their high reactivity. And option B is these materials react with lime in the presence of water to yield CSH. Again, that is true. They contain, we already saw that all these admixtures contain reactive silica, right? And when they come into contact with lime, calcium hydroxide, right, they start producing the CSH gel, right? And this is common in all the admixtures, and this is what is giving giving rise to the contribution of these admixtures to the strength of concrete, right? So that is also common. Option C is these have amorphous siliceous and aluminous content. Again, that is true. When they are heated to high temperatures and then cooled rapidly, they will have amorphous structure, right? And they will not be really stable. Okay, so those three are common for all the admixtures, whereas D, talking about shape, is not common, right? It varies. Okay, so question 14, we have 4 statements and we have to tell which of these statements are true. The first statement is rice ash has low specific surface compared to the other pozzolana owing to its cellular particle shape. Statement 2, slag floats over molten iron and is collected, granulated and ground to obtain GGBFS. Statement 3 is the role of the classifier in the production of fly ash is to separate fly ash by particle size. And statement 4 is in India, silica fume is a preferred choice as supplementary cementitious material owing to its low cost and relative abundance. So we have 4 options, so multiple statements could be correct. So the options are 2 and 4, 3 and 4, 2 and 3, and 1 and 3. Okay, we have 2 votes for option C. Okay, any other answers? Okay, so let's take a look at the answer now. So the right option is C, 2 and 3. Right? So statements 2 as well as 3 are true. Right? So statement 1 says rice has a low specific surface compared to other pozzolana owing to its cellular particle shape. So it's partly part of it is true, part of it is wrong. It has a cellular particle shape, that part is true, but saying that it has the lowest specific surface compared to other pozzolana is false, right? Because we saw that it has the highest specific surface, right? So we saw that was giving rise to the increased water demand and also the increased requirement of the plasticizer, right? So therefore statement 1 is wrong, right? It has high specific surface. Statement 2 says slag floats over molten iron. It is collected, granulated and ground to obtain the GGBFS, right? So that is correct. So GGBFS actually stands for ground granulated blast furnace slag, right? So that is how it is produced, right? If we, as we remember from the production of GGBFS, so that's how GGBFS is produced. Like we collect the slag from the molten iron, right? So and then it is ground and granulated slag is ground to obtain the GGBFS, and therefore it is true. Statement 3, it is about the role of classifier in the production of fly ash. So why do we use the classifier? Because we want to separate out the fly ash of different sizes. We want to collect the fine particles separately than the coarser fly ash particles. Therefore the classifier is the component in the production line that is responsible for this separation of the fly ash by its size. So 3 is also correct. Statement 4 is about the usage of silica fumes in India. So it says that silica fume is a preferred choice as a supplementary cementitious material, and the reason given is it is it has a low cost and it is relatively abundant, right? But this is false because we don't have silica fumes. Silica fume is not produced here, and therefore its cost when we are to use it as a admixture is higher, right? Because we don't have it in abundance here, and therefore the cost of it is higher, and therefore in our country it is not the preferred choice, right? From the financial perspective, right? So therefore statement 4 is also false. So only 2 and 3 are correct. So the right option is option C. Okay, so question 15, again we have two statements. We have to tell which of them is correct. So this first statement is pozzolanic material has a tendency to react with lime to form hydration products such as CSH. Statement 2 is pozzolana materials are produced as a result of heating parent material to high temperature and cooling it quickly to form amorphous material. So which of these statement is true? Either 1 or 2, or both statements are true, or neither of them is true. Okay, one vote for option C. Both are correct. Okay, another vote for C. Okay, any other answers? So let's take a look at the answer. So the right answer is option C. Both statement 1 and statement 2 are correct. Okay, so we already saw a statement 1, right? So as in the previous question, so the pozzolana material, they will react with lime to form CSH. So pozzolana, all the pozzolana material contains reactive silica. We already saw that. And during the hydration of cement, lime is produced, right? And when this reactive silica in the pozzolana comes reacts with the lime that is produced, it results in the hydration product, which is the CSH, right? So that is true. The rate of reaction will change across the material, but they will all react with lime to produce CSH, right? So that is true. So second statement is about the production of this pozzolana material itself. So again we saw that all these pozzolana materials are produced as a result of heating the materials to high temperature and also rapid cooling of this, and they will have an amorphous structure, right? So that is also common for all the pozzolana materials, and that statement is also true. So therefore option C, both statement 1 and 2 are correct. Okay, question 16, a numerical. A cement paste is prepared with 200 grams of cement. Fly ash is used as the mineral admixture for the given sample. At a given time, the degree of hydration is 0.75. So what will be the amount of silica that will be consumed in the fly ash? So the options are 24.5 grams, 21 grams, 22.5 grams and 30 grams. Two votes for option C, 22.5 grams. Okay, maybe one more minute for other answers. Okay, so I'll take a look at the answer now. Okay, the right option is C, 22.5 grams. Okay, let us see how we will get that. Okay, so based on the stoichiometric equation for the reaction of silica from this mineral admixture with the lime, so we know that the amount of silica that will react is 0.15 CH, right? So silica reacted will be 0.15 CH, right? So this is based on the stoichiometric equation, right? So the silica combines with lime to produce the CSH gel, right? So based on that, we know that we can find out that the amount of silica that will react, and that is about 0.15 CH, where C is the amount of cement that is used and H is the degree of hydration, right? So how much of the cement reacts, right? So based on this, so we need two pieces of information: what is the amount of cement and what is the degree of hydration. So both of which are given to us. So it is given that 200 grams of cement is used for preparing the sample, and at the given time the degree of hydration is 75%, right? So with that we will be able to compute how much silica would have reacted, right? So therefore silica reacted will be 0.15 times 200 grams times 75% of it is hydrated, and that if you solve it, it will be 22.5 grams, right? So that's how we find out how much silica will react for a given sample and also at a given time, right? So this will change because your degree of hydration will change with time, right? And therefore more silica will be reacting with longer time, right? But at a given time for a given degree of hydration we can calculate it using this equation. Okay, any questions? Okay, so moving on to question number 17. So which of the given two statements is true? So we have two statements. The first one is use of silica fume as a mineral admixture increases water demand in the cement concrete system. Statement 2 is silica fume has a very low mean particle size ranging from 0.1 to 0.3 micrometer. Thus, the high fineness requires large amount of water for wetting. So the options are only one statement 1 is correct, 2 is incorrect. Option B is 2 is correct, 1 is incorrect. C is both are correct and 2 is the correct explanation for 1, and D is both are correct but the second statement is not the right explanation for statement 1. Okay, we have two votes for option C. Any other answers? Okay, if there are no other answers, we'll see the right option now. So the right option is option C. Both statement 1 and statement 2 are correct, and statement 2 is the correct explanation of statement 1, right? So what are the statements again? So the first one says that silica fume has increases the water demand for the cement concrete system, right? So that is true, it increases. We already saw rice as cash increases it the most, but silica fume will also increase the water demand, right? So statement 1 is correct. Statement 2 is silica fume has a very low mean particle size, which ranges from 0.1 to 0.3 micrometers, right? And thus the high fineness requires a large amount of water for wetting, right? So that statement is also true. The silica fumes has a very low particle size. And what does this low particle size translate into? Because of the smaller particle size, the specific surface will be much larger, right? So because it is more fine, the specific surface will be larger, and when the specific surface is larger, you will need more water for wetting the surfaces, right? So because we have more surface to cover now, therefore more water will be consumed to wet these area, right? Therefore statement 2 is also correct, and statement 2 is also a reason why statement 1 is true, right? Because of this increase in surface area, right? So you are requiring more water, therefore use of silica fume is increasing the water demand for the cement concrete system, right? So both statements are correct, and 2 is also the right explanation for why statement 1 is true, right? So therefore option C is correct. Okay, so question 18 is again 4 statements are given. We have to pick which of these are true. So the first statement is fly ash decreases the water demand in the concrete due to ball bearing action and the spherical shape of the particles of fly ash. Statement 2 is the addition of fly ash reduces the heat of hydration in concrete. Statement 3, fly ash reduces the capillary pore sizes due to pozzolanic reaction. Statement 4 is fly ash increases the superplasticizer demand as more water will be required due to addition of fly ash. So we have 4 options. 2, 3 and 4 are correct. 1, 2, 3 are correct. 1, 3, 4 are correct, and 1, 2, 4 are correct. Okay, we have 1 vote for option B. Okay, 2 votes for option B. Okay, any other answers? Okay, so let's take a look at the right option now. So the right option is option B. Statements 1, 2 and 3 are correct, right? So all the first 3 statements are correct, fourth one is incorrect. So the first one says the fly ash decreases the water demand in the concrete due to ball bearing action and the spherical shape of the particles of fly ash, right? So that is true, right? So but we said that silica fume actually increases the water demand. It also had spherical shape, right? Similarly, fly ash is also having a spherical shape, but we are saying that it decreases the water demand. So why is that? Because the particle sizes are different, right? So in silica fume we have much finer particles, right, whereas fly ash has coarser particles relatively, right? So the even though the shape is same, because the sizes are different, the water demand is also different for fly ash and silica fume, right? So actually fly ash will decrease the water demand because of the spherical shape. They can also help with lubricating your concrete mixture, right? So it will help in reducing the friction when it is flowing, and therefore it will be more workable, and therefore you will need less water when you add fly ash. Therefore statement 1 is correct. Statement 2, it's about a heat of hydration. Again, we have looked at it many times. It depends on the reactivity, right? So fly ash is actually less reactive, right? Among all the different admixtures, fly ash has one of the least reactivity, and it will only start reacting when there is a sufficient amount of lime that is present in the system, right? So it's not going to react fast, and also therefore the heat that is released during its hydration process will be lesser, because it's going to take a long amount of time for reacting, and therefore the heat that will be released will also be distributed over a long period of time, and therefore at any point if you look at how much is the heat coming out, it will be lower, right? So statement 2 is also correct. Statement 3, fly ash reduces the capillary pore sizes due to the pozzolanic reaction. True. All the pozzolanic materials, they will help you in reducing the porosity, right? We saw that, right? So the pore sizes, capillary pores will be reducing when you add these mineral admixtures, and that is true for fly ash as well, right? And therefore statement 3 is also correct. And statement 4 is fly ash increases the superplasticizer demand as more water will be required due to the addition of fly ash. So this is wrong, but because it is just the opposite of what we saw in statement 1, right? So water demand actually reduces, but statement 4 says it will increase, and therefore the plasticizer demand will also be more. But that is incorrect, because your water demand is going to come down, and therefore the amount of superplasticizer that you need to add will also be coming down, right? So when you add fly ash, you should also adjust the superplasticizer amount accordingly, right? Therefore statement 4 is incorrect. So the right option is option B, where statements 1, 2 and 3 are correct. Okay, question 19. Again we have 4 statements. Here we have to find out which is incorrect, right? So the statement 1 is less bleeding is observed in concrete using silica fume as a mineral admixture due to pore filling effect and better microstructure. Statement 2, silica fume enhances the effect of air entrainment due to good water holding capacity. Statement 3 is silica fume provides high early strength as sufficient concentration of calcium hydroxide is not required. And statement 4 is silica fume can exhibit pore filling effect even on early ages due to fine particle sizes. So which of these is incorrect? Okay, the poll is launched. Whenever you are ready, please answer the poll. Okay, we have one vote for option B. Any other answers? Okay, 2 votes for option B. Okay, any other answers? Alright, so if there are no other answers, we'll take a look at the right option now. Okay, the right option is option B, which is statement 2 is incorrect. Okay, so let's take a look at each of the statements. So first statement says it talks about bleeding in concrete. So it says less bleeding is observed in the concrete when silica fume is used as a mineral admixture because of the pore filling effect and better microstructure. So that is true. So we have already seen that the use of the mineral admixtures is going to affect the porosity, right? It's going to reduce your porosity, right? So silica fume, it's also higher in the case of silica fume, like the pore filling effect, and therefore you will observe less bleeding, right? So what is bleeding? It is the water from the concrete, cement, sand and aggregate mixture that oozes out after mixing and placing, right? So when it sets after some time, so if you observe water coming to the surface because of its reduced because it is the least dense of all the components in the system, so that's what we call it as bleeding, right? But because of the reduced porosity with the usage of the mineral admixture, especially silica fume, we see that there will be less bleeding in the system, right? So therefore statement 1 is correct. Statement 2 talks about silica fume and the air entrainment. We already saw one question related to this. It says silica fume enhances the effect of air entrainment due to good water holding capacity. It's incorrect. We already saw that not just silica fume but all the mineral admixtures reduces the effect of air entrainment, right? So we saw that the air content is actually lower after the use of the admixtures, right? So again related to the void content that is present, right? So statement 2 is incorrect. Statement 3, silica fume provides high early strength as sufficient concentration of calcium hydroxide is not required. This is also true. Why it is providing high early strength? Because we saw that it is one of the highly reactive of among the different mineral admixtures, right? So because of that, its high reactivity, because it has very fine, it is very fine, it has high specific area, therefore it's more reactive. Therefore even with some amount of lime, it will react, right? It doesn't require a sufficient amount of lime to start reacting, right? As which is the case with GGBFS or fly ash, right? But for silica fume, that is not the condition, and therefore it can also contribute to the early strength of concrete. So statement 3 is correct. Statement 4, silica fume can exhibit pore filling effect even on early ages due to fine particle size of silica fume. Again true, right? So the pore filling need not just be coming because of the hydration product. Because of its fine particle size also, it can reduce the amount of pores or the volume of pores that is present in the system, right? Because of its size distribution itself, right? So therefore on in the early stages itself, you will see a reduction in the pores, right? So that again because of its fine size, right? So the statement 4 is also correct. So among the 4, only statement 2 is incorrect, therefore the right option is option B. Okay, any questions? Okay, so if there are no questions, that was the last question for this week. So we'll wind up the session here. If you don't have any clarifications or queries, right, I'll just stay back for a couple of minutes in case you have anything to ask, right? Otherwise, if you don't have any queries, you can feel free to log out. Thank you for attending, and we'll meet again next week. Okay, silica fumes effect on creep. I think we already looked at it, right? So silica fumes will actually reduce reduce the creep that you see, right? Why? Because it increases, silica fume actually provides high strength, right? You use silica fume and you require high strength. So because it increases your compressive strength, you will also see that the creep that you will see will reduce as compared to OPC when you add silica fumes. So its effect is that it will reduce the creep. Okay, any other questions? Okay, so let's wind up, and we'll meet again next week. Thank you.